Hey everyone, it's Mr. Anderson back with you again. Today we're talking about section 7.1.3 from our CPM Common Core Algebra ebook. And our goal today is to talk about growth, both linearly and exponentially, through a very, very common application in the real world, simple and compound interest. And the lens here that they give us is the lens of saving for college. And maybe saving for college isn't your thing, but hopefully everybody in all the viewership here hopefully is saving for something, right? It doesn't matter to me, what it is: college, car, down payment on a house, a rental, security deposit, whatever, saving for something. Okay. We're going to pay attention to starting values, right? We're going to pay attention to growth rates and multipliers. And then of course, we can look at some of these rates using decimals. And that's going to be an important thing as well. One more time, I'm going to focus on using Desmos for some of its non-graphing capabilities, but still for the fact that I can do some pretty spot on calculations for me. So I'll revisit that tool again today. All right, but we'll start today with section 7.1.3, but specifically problem 7-30, and I have that kind of pulled up in our notes here. And it says, suppose we have $1,000 to invest and know of two investment options. We can invest in bonds, which pay 8% simple interest. Simple interest is a very, very nice tool that banks incentivize you with to kind of keep your money so they can lend it out to other people. Simple interest is always going to be 8%, and your interest does not earn interest. The alternative is you can put your money in a credit union, which pays 8%. It looks the same, but this is compound interest, and that's going to be a bigger deal. Okay, it's going to grow differently because your interest will earn interest. Will the option you choose make a difference in the amount of money you earn? Examine the two situations below. Okay, so we're going to talk about bonds with simple interest. It says in part A, if you invest in bonds, your $1,000 would grow as shown in the table. How does your money grow with simple interest? Well, check this out, ladies and gents. We can do this. We've got on $1,000 starting value, we are growing by 8%. That's what we're told. Well, here's what I noticed. From here to here, I'm adding 80 bucks. I'm adding 80 bucks. And one more time, I'm adding 80 bucks. This to me means it's a predictable pattern. I'm going to go ahead and add another 80 bucks. That's $1,320, okay? And in case you don't remember in our work back from chapter 5, this is growth by adding, and I'm just going to make that note, by adding $80. And how does that growing? That's linearly. Okay, that means if we were to take all these points and we were going to plot them, they'd make a line, a straight line. And that kind of growth isn't bad because, as you see, year over year, we're making $80 more every year. And that's money we got for doing nothing, okay? But then they asked me in part B, and this is going to be pretty telltale, and we're going to want to pay attention. By what percent would your balance have increased at the fourth year? Show how you know. Well, here's how we figure out how our money is growing. We're going to take the amount we have in the fourth year, that's that 1320 number, and we're going to divide it by the amount that we started with. Ooh, that's a terrible looking line, Anderson. I'm going to try to draw that again. There we go. And you might be able to do that in your head, but in the event you can't, Desmos to the rescue. And I kind of brought this up in one of our last videos, that Desmos has a pretty powerful calculator right here. And I can just type this in, 1320 divided by 1,000, and it tells me that's 1.32. Okay, and that's not our growth rate, but it kind of contains our growth rate. Remember, this part right here is the amount that we're growing, right? And that's over 100%, because if I was to convert that to a decimal, it'd be 132%. Always I'd be returning 100 of those dollars, 100% of those dollars. But this part specifically right here means my growth rate is 0.32 or 32%. Over 4 years, that is not bad. And that is not a year-to-year growth rate. That is growth over 4 years, right? So got to be careful. Okay. The other option is the credit union option, and this is the compound interest. Okay, and let's go ahead and read Part C and make sure we're understanding what some of these compound features are. Instead, if you invest your $1,000 in the credit union compound interest that is compounded once a year, its value will grow as shown at the table on the right. Why is there $1,166.40 in your account in the second year? Explain how the compound interest is calculated. How in the heck is this thing growing? Well, the first one shouldn't be too bad, right? We're going to take that 1080 number and divide it by 1,000, and there is that 1.08, that 8%. But now let's take that second year value, that 1166.40, and then divide it by the number that comes before that. And I kind of already hinted at what I'm doing when I say it. I'm doing it that way. I'm hinting at the fact that this is an exponential growth rate. Okay, now check this out. This isn't exactly 1.08, but gosh dang it, it is pretty close. Okay, and this could be due to some rounding, right? Because we only measure money to 2 decimal places. So explain how the compound interest is calculated. How is it growing? Well, this is not growing linearly. Okay, in order to calculate the next year, and we'll do that here in just a second, I take the previous year, and I multiply that by 1.08. And one more time, this is my multiplier. All right, and that multiplier is, of course, the thing. 1.08 is the multiplier, but the 8%, sorry, is the growth rate year to year. And the key, and this is the difference between simple interest and compound interest, is that my interest is also earning more interest. And that's why we see this thing not growing linearly, we see this thing growing exponentially. All right, and that is the key difference. Now, you can see here that I got a little cut off there. I don't know what was going on here, but if we want to figure out what goes here, we can just one more time go back to our Desmos calculator here, and I can take that 1259.71. I can multiply that by 1.08, and that tells me it's $1,360.49. All right, it's not going to be perfect because I did have to round there, but there you can see that. Okay, what will that be at the end of the fourth year? Well, we kind of just talked about that. And then what would this account balance, by what percent would this account balance increase after 4 years? Show how you know. Well, we're going to do the exact same thing. We're going to take that 1360.49, and divide by 1,000. When I do this, I'm going to get about 1.36, and that tells me I have a growth 0.36 or 36%. And believe it or not, I know that doesn't seem super significant, but check this out. And I'm slightly off. There we go. Check this out. Here's my simple interest model. Here's my compound interest model. And when you're getting money for nothing there, you definitely want to make sure you're taking advantage of the model, that's paying you the most. So the compound interest model is the better option. All right, which account type, the bond with simple interest or the credit union account with compound interest, grows most quickly? And this is kind of a no-brainer now. We compare 32%, we compare it with 36%, and we're going to go ahead and we're going to say the credit union account grows faster. Okay, and if you've got the need for that money because college is not as far away as it once was, then you want to take advantage of the higher growth rate. Okay, number 32 here, we've got an idea that we're going to start to touch on here, and I want to make sure we give it enough time here. So we're going to check out number 7-32. Okay, so we're going to use the previous information with the bond and the credit union data. And as you can see, I took those two tables and I went ahead and I added them here for our convenience. We could have both of these things up to 4 years. Okay, and it says, think about the growth and starting point for the simple and the compound interest situations from the lesson. Model each of the two step functions with an equation. Let y represent the money in the account after X years. Now, we're going to go ahead, as we already discussed. This first one is linear. Okay, we do have a starting value here. Okay, and I'll remind you that the starting value is my intercept. Okay, so I'm just going to plunk that out there as my intercept, and I'm growing, recall, by $80 every single year. So that's a growth rate of 80, or I'm adding 80 every single time. That's my slope. So for this linear bond model, this is the equation that I can use, and that works pretty well. The credit union model is going to be an exponential one. So one more time, we do have that starting value of $1,000, so y equals 1,000. But then because we're growing exponentially, we're not going to use necessarily a linear model. We want that y equals ab to the x model, where my growth rate, because we're growing 8%, is 1.08 to the x. Okay, so here's going to be my model for the bond model. And what I did is I just went real quick to Desmos and I graphed these things. And I didn't do anything special. I just graphed them using the table features in Desmos. But now what I'm going to do is I'm going to add the lines that we just kind of discussed. 80x plus 1,000, and that data was orange, so I'll make this orange. And then I've got y equals, what was the other one? 1,000 times 1.08 to the x power, and that one's purple, so I'll make that one purple. And just as soon as 4 years, you guys can see that these two lines are not the same, right? We can see those two things start to differ, okay? And we're going to use this graph here for some what's called predictions here, but you can see I also took it and I tried to model it here in part B, where I added that info, and I could maybe extend it out a little bit if I wanted to. I have enough space for that, but I don't necessarily need to. And what we're going to go ahead and do here is we're going to talk about letter C, where it says use your model to predict how much your original $1,000 investment will be worth at the end of 20 years in the credit union. And this actually isn't too bad because of Desmos. I can do this one of two ways. The credit union's the purple. I can go ahead and I can continue to do this and continue to multiply by 1.08 using the table. Or because I have this line now graphed, because I put this in here, I can just kind of like extend this out. I'm going to zoom out a little bit so we can see. I'm going to make sure we can get out to 20 years, right? I just want to see 20 on my graph. I want to see that purple line where there's 20, right? Okay, and what I can do is I can just kind of click using Desmos, and I can get that x value as close to 20 as I can. Here I was able to nail it. All right, and that tells me $4,660.96. That is going to be a perfect $4,660.96. That is going to be a perfect prediction. Okay, I could also use my model like this, and it would be a little tougher, but I could do it. I can, instead of putting in the x, I could plug in a 20 there, and it would give me the exact same thing, right? Or it should give me the exact same thing, okay? As long as I'm following my order of operations, right? Part D says, why are your equations considered a model instead of a representation of real behavior? Is there an advantage to using a model to make a prediction? Well, folks, we always try to use models with accurate data to make predictions because it informs our decisions, all right? But real market behaviors, they don't necessarily always behave constantly the same way every single time. So that's why it's a model, and that's why it's a prediction. We have to interpret it as such. And of course, the fact that I'm using a graph does the exact same thing. It's for predictive purposes. I've got just a little preview here for you guys, 35 to 38. I'm going to ask that we all give this a shot, and we're trying these things so we know what kinds of questions that we can ask. Ladies and gentlemen, thank you for watching. Have a great day.